Welcome to Circuit and Soul. Today, we dive into the heart of artificial intelligence. Can machines truly learn on their own, just like we do? In traditional AI, you had to manually code hundreds of rules just to identify a cat, if the ear is triangular and the nose is small. But when faced with thousands of different cat and dog photos, the system would collapse. There were simply too many rules. The old system would throw a failure at the slightest variation, overloading the entire system. Is it a cat? Is it a dog? It couldn't decide. This rigid approach was insufficient to solve the complexities of our world. Teach it how to create its own rules. That's where the solution lies: a neural network. The Octobot is depicted floating in a dark, glowing void, acting as the living neural network. Its translucent body clearly displays three vertical, distinct layers of connected nodes and lines, neurons, synapses, within its structure. The left layer is labeled input, bright green glow. The central, more complex layers are labeled hidden layers, pulsing purple glow. And the right layer is labeled output, sharp blue glow. The Octobot's tentacles point to the layers to emphasize its control. Detailed sketch art, comic book, high contrast, cyberpunk aesthetic. Unlike the old system, we don't code the rules. Instead, we feed the Octobot massive amounts of data and let it figure out the connections between these layers itself. But why do we call it deep learning? Because the magic lies in the number of hidden layers. A shallow network, with only one or two hidden layers, is very limited. It can only solve simple problems, like detecting basic shapes. To solve complex tasks, like truly understanding an image or a human sentence, we need dozens, sometimes hundreds, of these layers stacked on top of each other. The more layers you have, the more detail the Octobot can process. Think of it like this. When a cat photo enters the network, the first hidden layer only sees basic edges and lines. The second layer combines those lines into more complex shapes, maybe a nose or an ear. The middle layers recognize patterns, the shape of an eye or the texture of fur. Finally, the deepest layer processes all those components to confirm, this is a cat. This process of automatically breaking down a complex input into its fundamental features is the power of deep learning. But how does the machine get better? It uses a powerful technique called backpropagation, or learning from mistakes. First, the Octobot makes a prediction, say, cat. The Raven bot, our guide, checks the ground truth and instantly sends back a signal, wrong. That was a dog. The network now knows its prediction was off, and it needs to adjust. This error signal then flows backward through the entire network, a process called backpropagation. It calculates exactly which connection, or weight, contributed most to the mistake. The Octobot uses this information to adjust every single connection across its layers. The next time it sees that data, the path to the correct answer will be stronger and the path to the mistake will be weaker. Over thousands of examples, this constant adjustment is how the machine learns to be accurate. The Octobot has successfully learned to identify the cat, but it brings us to the Raven's observation. We still don't know exactly how it decided. The network is so complex that even its creators cannot trace the millions of connections that led to the final answer. This is the black box problem, where the AI's decision is opaque and unquestionable. Deep learning is revolutionizing how machines see, hear, and think, but it constantly challenges the line between code and consciousness. Join the Circuit and Soul journey as we continue to unpack the logic and define the legacy of technology. If you enjoyed this analysis by the Octobot and the Raven bot, hit subscribe. Next time, we ask, when will the machines achieve full AGI?